Section 9.1 is quadratic graphs and their properties. I can graph quadratic functions of the form y equals ax squared and y equals ax squared plus c. Big ideas here. The family of quadratic functions models certain situations where the rate of change is not constant. Quadratic functions are graphed by a symmetric curve with a highest or lowest point corresponding to a maximum or minimum value. Take note, talked about the standard form of a quadratic function, which we've talked about before. A quadratic function is a function that can be written in the form y equals ax squared plus bx plus c. So we talked about expressions in standard form last chapter, where our biggest variable is first. Here it's a function because it's equal to y, or equal to, we could do f of x as well. And it's quadratic because our exponent is a 2 in our first term there when it's in standard form, our leading exponent. This form is called the standard form of a quadratic function, so ax squared plus bx plus c. The simplest quadratic function, f of x equals x squared or y equals x squared, is our quadratic parent function. Okay, it hasn't been moved left or right or stretched or compressed or flipped or anything like that. That's as simple of a parabola, which is the U-shaped curve that we get from a quadratic, that we can get. And that's shown on the bottom of page 546 in your book. The two sides of a parabola are exactly the same. They're mirror images or symmetric. And the line that splits the parabola into matching halves is called the axis of symmetry. The highest or lowest point of a parabola is called the vertex, and the vertex is always on the axis of symmetry. When a is greater than 0 or positive, the parabola opens upward. On my back wall I have a happy face poster, so a happy face parabola. The vertex is the minimum point of the parabola. It's the lowest point here. When a is less than 0 or negative, the parabola opens downward. And we have a maximum point there. That's the highest it'll ever be. So if a is less than 0 or negative, the parabola opens downward, and we have that maximum. If a is greater than 0 or positive, we have a happy face parabola. It opens upward, and there's a minimum point. In example 1 here, we want to know what are the coordinates of the vertex of each graph on page 547. Is it a maximum or a minimum? So in A here, we are dealing with the red graph. So our vertex is always on our axis of symmetry, and that's the point where our graph, our two branches, if we folded them on top of each other, would land right on each other. It's like if one side was drawn with wet paint and we folded our paper in half, we'd get the other side. So here in the red, the coordinates of that point are x is 0, y is 3. We want to know, is it a maximum or a minimum? Here, that's the highest our graph will ever go. It's a maximum. Okay, our graph will never go higher than that point. And when we're talking about maximums and minimums here, we're talking about our y values. Our y value is never going to be higher than that. As far as B goes, the blue graph, our vertex is at 1, -1. And because this is the lowest our graph is ever going to go, if we look, our branches go up. Okay, this is going to be a minimum. It's never going to go below that point. Now, feel free to pause here and give this a try if you'd like. We want to know, what is the vertex of the graph in the middle of page 547? And then is it a maximum or a minimum? Here our vertex is our highest or lowest point. Here, that happens to be right there. My x value is -2. My y value is -3. So -2, -3 are the coordinates of my vertex. Now, because it opens up, okay, our branches continue up, that means that our vertex is going to be the smallest value we can ever get, and that means it is a minimum. In example 2, we're going to graph this function. And as always, when we get to functions that we're not really sure how to graph, they're not in slope-intercept form, for example, or something like that, or not a linear function, we can use a table of values. So here, I'm going to pick x values and plug them in to find my y values. I'm going to use -2, -1, 0, 1, and 2. And those are going to be the most common places for us to start because when we square numbers, they start to get pretty big pretty quick. So if we use these values here, it's going to make it a little bit easier to fit them on our graph. Now that we know our x's, we substitute them in. -2 squared is 4 times a third, 4 thirds, or 1.3 repeating. So at -2, I'm going to have 4 thirds. -1 squared is 1 times a third, 1 third, or 0.3 repeating. 0 squared is 0 times a third, 0. And we've done these table of values before, guys. All I'm doing is taking my x value and substituting in it for x in my function. And the value that I get is my y. Then, once we have our dots, we can connect them. Let's try that again. Keep in mind here, guys, we want this to be that curve, that U-shaped curve. Not going to be a straight edge. Okay, we're not going to use a straight edge to connect these, not going to be lines. It's a curve. Both sides should be symmetric, which means we should go over the same amount and up the same amount. So same distance away from our axis of symmetry here that cuts our graph in half. And I know these are hard to draw, guys. So what I'm really looking for are your points. I want you to also make sure that you're trying to make it curved. Okay, we don't want them to be lines in between here. We want it to be curved. And to make sure that your arrows go out and up or out and down, if that may be the case. We don't want them to come back in like this. Okay, we don't want them to come back in. So be careful there. Now, we need our domain and our range. Domain deals with x's, range deals with y's. And if we look here, guys, are there any x's that we can't plug into this function? No, we could plug in any number we want. And if we look at our graph, we can see that as well. Because we have a continuous graph here. Okay, it's one big line. And it goes in both directions. So we're going to keep getting bigger x's and smaller x's here. So all real numbers. And that's always going to be the case for quadratic functions, unless it's some type of an application that excludes things. But for a base quadratic, that is going to be our domain. As far as our range goes, guys, that deals with y's. So here's going to be all real numbers. But if we look, guys, there are some numbers I'm just never going to get. We've talked about this a little bit already. We said that our vertex is either our maximum or our minimum. Here it's our minimum because it's a happy face positive parabola. We're never going to get smaller than 0 for our y value. So our values are going to be greater than or equal to 0. We can't have anything below. So greater than or equal to 0. Here's a little bit of a spoiler alert on your ranges. So your range, when we have a happy face, which makes it a minimum, it's always going to be all real numbers, greater than or equal to, and then the number that we plug in here is going to be the y coordinate of vertex. The y coordinate of your vertex. Okay? If we have a sad face parabola, which gives us a maximum, our range is always going to be less than or equal to, and then whatever value you have for the y of your vertex, the y coordinate of your vertex. Okay, so a little bit of a spoiler alert for you there. Now, feel free to pause here and give this a try if you'd like. We need to graph this, and in order to do it, we're going to use a table of values. I substitute them in. And again, we're going to make sure that we plug those into parentheses. Anything squared gives us a positive value. So negative 2 squared is positive 4. Negative 2 times negative 2. Negative 1 squared gives us a positive 1. So then we multiply by negative 3. 0 squared, 0 times negative 3 is 0. 1 squared is 1 times negative 3. And 2 squared is 4 times negative 3. Again, all I did is took my x values, substituted them into my function, and solved for y. Now we're going to actually draw in our points. This is a negative 12. I think I missed that. Sorry. Negative 1, negative 3. 0, 0. 1, negative 3. And 2, negative 12. I also could have used a scale here, guys, and that would have worked as well. Again, try and make that curve a little bit so it goes through that point. These are hard to draw in, guys, and I recognize that. So I'm going to be mostly looking that you tried and that you have your points down so I can see where you were supposed to be going. A little bit better there. Okay, so there's the graph. My domain, again, I can have any number that I want to plug in. There's no number we can't square and then multiply by negative 3. My range, however, there are some values that I'll never get. Here I have a sad face parabola, which I should because of my negative in front. Okay, the negative tells me it's going to be a sad face parabola. So I have a maximum value here, which means all of my y's are going to be anywhere less than or equal to the y coordinate of that vertex, which is 0. In example 3, we're comparing the widths of parabolas. We're going to use the graphs on page 548, which I kind of put here. 548 has obviously better pictures. Mine are really wobbly. I can't get my pen to do them a whole lot better than that. But we're going to go with it anyway. So what is the order from widest to narrowest of the graphs of the quadratic functions? So the widest one here is in blue. Okay, and you can see that better on the pictures in the book as far as comparing it to the red. But the blue one here is widest. Okay, then we have the black function here, f of x equals x squared, and the narrowest is our red function, f of x equals negative 4x squared. So something to consider here, guys, that's because of our a values, our numbers in front of our parentheses, which remember, or in front of our x squared, which remember, if there isn't one, is a 1. And the 4. We don't worry about the negative there. That tells us happy face or sad face, but doesn't tell us anything about the size. So the smaller the value, smaller the a value, okay, the number part, not the sign, the wider it's going to be. The bigger the a value, the narrower it's going to be. We call those stretches and compressions. If it's less than 1, it smushes it down as a compression. If it's greater than 1, it stretches it out and makes it really narrow. So here, what is the order from widest to narrowest of the graphs of the function f of x equals negative x squared, f of x equals 3x squared, and f of x equals negative 1/3 x squared? So here, guys, again, we're just looking at the number parts, not the signs for our a value. So I know it's a negative 1/3 here, but we're looking at just the 1/3. Here, remember there's a 1 there, and we're just looking at that, not the negative. This tells us those will be sad faces, but we don't worry about that right now as far as wide and narrow. So our widest is going to be our smallest value, the 1/3. Then our next smallest value is 1. And our biggest value is the 3. So 3x squared is going to be our narrowest. And I will stop here and continue in another video.